And I think we saw this in the class, but I'm going to play it anyway. Are you able to hear the audio from this video? Using the default example from the Arduino IDE. You can see how the poles are being pulsed. In order to achieve the step, this is the ULN 2003. I don't know if you can see the back of the system here. I've hooked up the wires so that they're going into poles digital outputs 8, 9, 10, and 11, just the way it is in the example. You must hook up power. For power, I use ground and 5 volts. The ground and 5 volts go into the -5 and the minus and the plus respectively. So minus is for ground, plus is for 5 volts, and then you put your jumper onto the other side. If you don't have the jumper on, nothing will work. I can pull it to show you. See, busted. So you got to have that jumper. But other than that, there's no real trick to getting these things to work. The examples work right out of the box. Thank you. All right, so you've got that in your background now, and of course you had the lab on the stepper, and that kind of makes everything relatively timely. So then we modified the standard program to go from a speed of 60 to a speed of 30, and things started to work properly. One thing I would point out is that stepper motors require more current than Arduino Unos like to supply. I'm not exactly sure I remember how much current you want to draw from an Arduino, but it's not much. Max current from an Arduino Uno data pin. It's quite limited. 40 milliamps. Okay. 40 milliamps. You know, you can do a lot with 40 milliamps. You could probably drive a really small relay. But when you consider that what you've got with the Darlington transistor array in the UL 2003 is the ability to draw like 1,000 milliamps, that's kind of a big deal, because now you can drive a rather large relay or other loads like a doorbell or a anything that needs substantial current. You can't really do much with just 40 milliamps. You need to amplify it, and that's what the Darlington transistors are all about. And that's kind of an interesting idea, and it kind of comes from electrical engineering, but when you do a course like this, you operate at the intersection between electrical engineering and computer science. It's more like computer engineering than anything. So having that skill in both areas is kind of important, and it lets you interface to stuff. I don't know what the issue was with the I guess you could say, I kind of know what the issue was with being able to turn backwards with these relays. We took it apart. I don't know if you were around for that, Chris and I think Chris mostly took the thing apart with a ginormous channel lock pliers, just squeezed the case until it popped with a pretty broken looking stepper motor. And we did a little autopsy on it, and we found the plastic gears were kind of worn down, and if you tried to turn it counterclockwise, it bound up and just didn't work properly, but it was completely mechanical issue. It had nothing to do with the software. And so what we got there was kind of a problem, mostly I would say with the construction of the motor and its gearing. These motors are geared so that you get like 4,096 steps per revolution. So they're very precise, but they only want to go in one direction. And that's a bit of a problem. Let's see now. I'm going to see if I can get back to Blackboard without the answer key showing. You know what I'll do is I'll just start a new window. That's the best. Just kind of want to cover the homework that you're going to be seeing. So this will be homework number 9. Oh, here it is, homework number 8. And let's just do a begin and see what it looks like. All right, so we took the opportunity to take apart a stepper motor. I hope you were there for that, but if you weren't, are stepper motors regarded as brushed motors or are they brushless motors? How do these stepper motors work? Any ideas about that?
They're geared up brushless motors, right?
That is correct. These are brushless motors, and I would guess that you guys already know what a brush DC motor is. But I'll see if I can find a nice picture. Well, certainly you've seen these little guys. They're in toys and such. But you should be able to see what's going on inside. Usually there's a commutator that goes around the part that turns, which we call the rotor. Here's a nice blow-up diagram. The rotor core. Let's bring that up. I like that picture. Stop it with the advertisements. Let's see if we can there we go. So these brushes, right, are actually making contact with the electromagnets that are a part of the rotor. They call them rotor coils. The alternating electromagnetic field is changed in its polarity every time the shaft is turning, because the commutator, which is these coppery looking things, hit the brushes and changes the orientation of the magnetic field. As that happens, there are these magnets, permanent magnets, which are mounted on the outside housing. These are called, that's called the stator. Stator is the part that stays, right? That's hence the name. Rotor is the part that rotates. This is a great looking name, great looking picture, but it's not always this way, right? Because what happens if you find yourself looking at the high performance motors that some of the drones use? I know you've seen some of them. They'll actually invert it so that the electromagnets are on the stator and the permanent magnets are in the are on the rotor. Now that's an interesting way to go, because what that means is you really don't need a commutator, right? You can just electronically switch the coils and start to get them to rotate around the magnet, just like a high-speed stepper motor. So those motors have a different philosophy of design, because without a commutator, you've no need for brushes. If you don't need brushes, there's one less moving part to wear out. And when you think about like the stepper motors that we have a few moving parts in there because it's geared. But if you wanted to minimize the number of moving parts, you would have an ungeared stepper motor, and you would simply rotate the permanent magnets by alternating how you energize the electromagnetic coils. I don't know if we can find a let's use the Google and find one. Drone DC motor construction. They use special controllers, but most of the time those controllers are electronic nowadays. And so, yeah, this is actually a cool one for aircraft. You can see all the electromagnetic coils are going around the rotor, and the permanent magnets go on the inside. And that kind of makes sense in a way, because then you don't need to have any wires that are energizing things in the part that rotates. And whenever you have wires that go in there, you need a commutator, or else, well, or else the wires get all twisted up as it rotates, and you don't want that. So that's a different design. It's kind of an interesting one. Let's see now. Here's one where the magnets are on the outside, but putting the magnets on the inside, that's kind of a nice way to go. And it is I don't know, I'll say a classic way to design these drone motors. So here's a drone motor. This one has magnets on the outside. They should have one with magnets on the inside as well. Let's see if I can find another one. This one probably has magnets on the inside. Some of them you'll see the construction is obvious. Others not so obvious. Let's see if they have another one. I'm not seeing it right offhand. But that's another, they call these brushless motors. There it is, brushless motors. So the brushless motor like this is a very high performance motor. It doesn't have a commutator, can have extraordinarily fast rotational speed. And because it's brushless, you don't have to worry about the commutator wearing down the brushes. And in fact, you don't have a commutator. So that's kind of cool. So brushless motor has more in common with a stepper motor than than the brushed DC motor does. In other words, the switching that occurs in the electromagnets for a brushless motor is electronic. The switching that occurs in a brushed DC motor is electromechanical. And so the electronics is a little bit more expensive and more complicated on the brushless motor. And you've seen what it takes to put out a binary number in order to get the shaft to do the rotation. And so that is, at least in part, what it takes to build the driver for a brushless motor as well as a stepper motor. So that's kind of interesting. So that's my little shtick about brushed DC motors. So the answer to that question, I know it's a little bit long-winded, but it actually had a good lesson in it. These are brushless DC motors. And if you haven't had, a course that involves learning about motors, this might be one of your first experiences with motors. And motors are kind of important. You'll find them everywhere and use them in all sorts of interesting projects. Now, the number of steps in a stepper motor are fixed and equal. What do you think about that? Any ideas? I'm going to see if I can get the chat facility here, because I have a feeling people just don't want to pipe in. But I'm thinking the chat facility. Here we go. Yeah, nobody's saying anything. Someone want to say something in chat? Would it be more comfortable if you just typed it in? What do you think? Can I change the number of steps, the number of mechanical steps in a stepper motor? And the answer is no, right? They're geared sometimes, like we saw, but once the gearing's in place, unless you throw in a transmission of some kind, the number of steps is fixed, and the number and their spacing is equal. So that is a true statement, right? Stepper motors have fixed and equal steps. So now we've played with servos, and we had a little lab on stepper motors yesterday. Servos work because they have feedback, right? In other words, the shaft encoder goes into a little potentiometer, and the potentiometer tells us where the servo is positioned. And so when we tell it to position in a specific place, it's always hunting for a specific orientation. Whereas stepper motors are different, and they often do not have an encoder on their shaft. Instead, we tell them to go so many steps, and then they just move in that way. And that's called open loop control. So there's two kinds of control: open loop control and closed loop control. Open loop control, you give a command and the plant obeys the command. Whereas closed loop control, the plant can go to a specific location but requires some kind of a sensor for feedback. And so servos have that sensor built into them often. If you had the joint angle for a robot arm such that it had an optical encoder, you'd know the angle of the arm, even if there was a heavy payload in the gripper. And that's important, right? Because you could probably get the servo to work reliably on an unloaded arm, right? But if you don't have any feedback at all, kind of hard to position the arm in an absolute fashion if you don't know what the payload at the end of the arm is going to be, because as the arm is extended, that payload is going to have a, well, I hate to say it, moment arm, right? It's going to apply some torque to the, I'll say the shoulder of the robot arm. So you've got to, in some sense, have some kind of feedback. It might be a vision system that's overhead, so you can see, like if you're picking up a pawn, where the pawn ends up with your little gripper and arm, that sort of thing. So if you have vision, vision can act as your feedback and can close the loop. A lot of times you'll see industrial robots that are really precise. You can position them without having any feedback, and they do open loop control, but they're not going into a bin and picking out parts at random. For that, you need some kind of feedback. You've got to probably use a vision system. So then here comes brushed DC motors rotate continuously when AC voltage is applied to their terminals. And it looks like there's a link. I think you can click on it. Yep, here it is. And you can read all about brushed DC motors. And here you can see a motor turning. And what's going on here is the commutator is inverting the orientation of the electromagnetic field in the coils. So this is kind of a nice page, actually. I sort of want to take a look at it just to make sure. Yeah, it's got a detailed explanation of how motors work. And that is a really cool thing. So how do you change the direction of a DC motor? Let's say it's moving clockwise and you want to make it so it goes counterclockwise. What do I do?
You change the polarity of the voltage you are applying across it.
Great. So suppose I want a switch to change the polarity so that the plus side goes to minus and the minus side goes to plus, and it does it in such a way that it doesn't create an intermediate short circuit because those motors could take substantial power. They could be several horsepower, for example. They could be motors that run your dryer, for example. They could be motors that, I don't know what they do. They start your airplane. So and how would you create a switch that would allow you to change the direction of a DC electric motor's current? I don't want to just unplug everything and plug it in backwards because I know that's going to work, but I want to just flip a switch to do it. And the answer is you need an H bridge. This is a good electrical engineering thing to know. This is a, I'll call it a semiconductor implementation of an H bridge. But here is the schematic. And what you can see is if you close S3 and then close S4, the current will flow in this direction. But if you open S1 and open S4 and then close S3 and close S2, the current flows in the other direction. And when you do that, you have an opportunity to change the direction of the motor. So it's really based on 4 switches. And these are electronic switches when you have a semiconductor implementation of your H bridge. And in fact, you can see there's even a chip in here for doing it, and it's able to switch up to 600 milliamps. But of course, some of them will switch more, and you can see this guy has a big bulgy heat sink. I think we have a few of these kicking around somewhere. So an H bridge is kind of an important thing if you're just doing a straight DC motor and you want to invert the current. Now here's the semiconductor implementation right in through here. We're going to use the current controlled transistors known as the bipolar junction transistors, or BJTs, and we'll put in a current, and that's going to allow us to make a connection in here. We'll put in a current here on Q4, and that'll make a connection in through here. And then if we want to, we withdraw those currents, which will essentially open up the transistors, and then apply currents to Q3's base and Q2's base, and that will enable the current to flow in the other direction. So that is a transistor implementation of an H bridge. All right, that's a solid state implementation, whereas this might be an electromechanical implementation where you have cross-linked, I guess you would call this single throw double pole switches, STDP, single throw double pole. So if you had 2 single throw double pole switches, you can switch this one closed, and then you could switch it opened and then switch the other one closed. But if you had them both closed at the same time, that wouldn't be good, because then you would have this voltage directly connected to its negative side, and we in the biz call that a short circuit. So you need an electromechanical apparatus for doing this that keeps one set of switches opened while the other set of switches is closed. You could do it with a relay. You could do it with transistors. I guess you could do it with tubes, but I've never seen anyone do it with tubes. So that's the bird's eye lowdown. Here it is with MOSFETs, and so they're relatively high powered voltage variable resistors, and MOSFETs can make a nice H bridge. What do you suppose these diodes are for in here? D3, D4. Somebody thought to put in these diodes. What's that about? Any ideas? What do you need diodes for? If I was going to power the coil for a relay, here's the hint, I would still not want to have those diodes across the coil. And the answer is, when you have a collapsing magnetic field, it creates a back EMF. That back EMF can damage transistors. And so you can short out that back EMF, which is a brief impulse, but can be quite high in amplitude, using these diodes. So that's why they put the diodes in there. So that's kind of an interesting little artifact. And you'll see those diodes in relays as well. Once you start driving things with power, all of a sudden you're worried about, the actual back EMF that's generated when you've energized a coil, and then that energy collapses. And so you can basically protect your electronics. Here's an example with BJTs with your diodes. So this is another example where if there's a current that comes in from collapsing magnetic fields in this motor, it doesn't go across the emitter and collector of this PNP transistor. Instead, it goes and shorts out to the supply. So that's kind of cool, and that's good to know. So let's see what else we got here. So the answer to this question, question 4. Do brush DC motors need AC voltage? The answer is no, right? Because why? Because as we've seen, we have a commutator that allows the electromagnets to change polarity, and therefore we don't need an AC voltage in order to be able to change polarity. We are already doing that, making a kind of pulsed direct current, PDC, in order to be able to get the brushed DC motors to rotate either in one direction or the other. So we invert the direction with DC using an H bridge, or we can keep the direction going in the same, let's say, clockwise fashion using DC current, right? Direct current. So I don't need AC if I have brushes, right? I can run them off a battery and that'll be fine. And that's typical, right? So what's a stator? We kind of did this, right? You guys can pipe in with the chat if you like. What do you think a stator is? Right? There's a rotor, and there's a stator, and those are the two basic components of any motor. Right? There's a part that rotates, and there's a part that doesn't rotate, and the part that doesn't rotate stays. Hence the name stator. And if you have a housing that you want to nail down to a printed circuit board, it would be really bad if that housing rotated. You wouldn't like it, right? Because that means it pulled out of the board. So let's take a look here and see what else we got. Oh, here's a nice picture. So here's the rotor inside here, and that's the moving or rotary part of a motor. Does that sound true? I know you guys know this by now, but you can't just sit like lumps on bumps. It's not good.
Is that true?
Yes, that is true. That is true. Right? The rotor is the part that moves. The stator is the part that does not. And you can tell it doesn't move. Why? Because it's got these big bolt holes in it. Right? Someone's going to have to bolt. I don't know how many horsepower this motor is. It looks big. But someone's going to have to bolt this thing down to keep it from, I don't know, tearing itself apart when you first power it up, and perhaps when you put a load on the shaft. I mean, if you think about it, motors are so important, right? I mean, they're everywhere. Sometimes they're little motors that make your phone vibrate. Sometimes they're huge motors that'll let you drive in an electric truck or something. And you can have all kinds of motors. Tesla makes motors that are perhaps efficient. And let's see. And we use a motor every day when we start the car, right? That's going to be the alternator set up or the starter set up to actually turn over the engine, because unless you're driving a Model T with a crank,